when the zero equal to 0. So x equal minus 2. X equal minus 2 is here, right? And it's 0. Form is when the denominator part is 0. So the root of this one will be complex number. That's why you have here and there. Okay? Any other questions up to number 8? Okay, let's go back to project number 10, 9, we enter up to number 8. Number 8, we did it number. So now you next thing is include I control integrator, okay? So I'm going to have open my program. Let's see project number 2013. Come on, so simple. This guy. Let me ask you one question up to number 1 over 5 of this. Find, not here, number 7. So constant closed loop, find the gain KB to reduce overshoot less than 5% when K equals 40. Anybody, what is your value actually? Anybody got it there? Okay, what value you have?
Well, so long as we start with the same time constants in step 1 rather than what we did in class, it was a gain of 10.
Gain of 10, anybody? Didn't try it yet? More about it. You gotta start quick. Okay, today probably at least each team has one computer, isn't it? Is it true? Anybody didn't? Your team, any team doesn't have computer? There's no computer over there. You guys still have it. I like to show how you can see. Actually, you got the program working, okay? Before I go home today. Okay, now, so I assume you're gonna do it. After I finish up this one, you're gonna do it together. So I'm going to add integrator part, okay? So let's go to...
Tim, was 10 right for the gain on 7 or not?
It depends on your simulation.
Oh.
10 look like right. About right. Okay? So now, I'm going to add integrator. So what I need to do is, simulink here. Oh, I did open simulink here.
Oh, but for the class example, we found that KD needed to be 5. It's like 0.1 right now.
Probably 5 is sure work too, I believe. So I'm going to have integrator. So it should be error integration of this. And I'm going to multiply gain. So it's a KP is 100. Control C and V. So probably I'm going to, before I go here, I'm going to verify quickly with you guys. So let's make KI is temporary 0. So it's still PD controller. So now if you run this one, it's a 0.1. So what is my time constant? Exactly is not, I use 0.2. 19 was 0.2. What was it? 0.24. About 0.2. And generator is 4 seconds. Okay, good. So I'm going to run this one first. Say what is the overshoot? What? there's error there. There should be some kind of error. No, it's not. No, it's not error. Excuse me. No. Next one. Yeah, here. So let's have this one. So it's more than, obviously more than 5%. So I'm going to increase about the 10. That the refund is 40. So I'm going to make 40 first. The given again. So your response again, let's see. So it's about the 20%. Right? So I'm going to increase about 10. And you said the 5? So let's start with 5. So if you run this guy, yeah, 5 is working fine. 10 is a graceful way to do it, but 5 working fine. 4 minus 6. Okay? But your case is a 0.5, so let's take it out. 0.5, what do you have here? You sign in the 0.5 initially. If you have 0.5, how much you need to have it? It's more than 5%, so not gonna work. Okay, for your case, probably not gonna work. 5, not gonna work. So I can increase about 10, because she found there also. Let's see, 10. So did it work? So what is the value here? So let's say 5%. So basically, it's about 8 or 7 is probably right. 8. Not gonna work. 9. So you try the letter. So 9 doesn't work. So minimum is 10. So 9 point something should work. Okay? You just use 10. It should be okay. But system 1 and 3 will be different numbers. So, okay? So now I'm going to still, if you 510, you run in this side, you'll stay like this much here. Okay? So now, if you integrator, I add this one to like 5. So you run this side, so your state right is 0. It's not high yet. But it's less than 3%. So I can, if you increase by 10, probably gone. Oh, sorry, there are too many data. So I'm going to change this one to no limit. Sorry, no limit. So we can copy everything. You run it. So it's that. So what is the Saturday time? Is that a 2% or 5%? Did I say 2% or 5%?
I've been traditionally 2%.
Yeah, it's no, it doesn't matter. It didn't say anything on there. So let's make it like a 2%. Okay. Final conversion system is again you do here. So you can make you can discuss 2% Saturday time. With 2% Saturday time. So what is the 2% Saturday time for my case? So it should be 0.98, right? Somewhere here. 0.98, so way back. So, well, somewhere here already. Yeah, it's already there. So it should be Saturday time is somewhere here. 0.92. So here, about 2.1, right? So and you need to make sure it starts to the 1. So you're settling time about 1 second, right? Because you have to count from here to here. So it's about 1 second. About 1 second. Okay? Questions? Yes.
How was it working out? Where did you count from the...
Because step of time is 1 second. So from 1 second to here, then interval will be about 1 second. Okay? So we can discuss that one. It does it have a state data with the lamp input? Yes or no? So let's go try lamp input. So instead of step input, okay, instead of this, I can use lamp input. So there's the source here. And there is lamp here. So instead of this, let's use the lamp. So the step should be starting to, let's start time with the 1. So slow with the 1. Okay, so every 1 second it will go up. So you go here. So your output will be like this. So there is, actually, if it's, what is the ideal?
It would be a perfect slope of 1 if it was...
Yes. So you can find here, ideal is, now I can use input and output together, right? So you can use a mouse. Yes. I'll take it here. The output. That's it. Okay. Your input is this one. So you run this guy, you can see both of them. Yes. So definitely there is error here. It's not this there. Okay. So even if you PID controller, it has error. Okay. Lamp input, it has error. To get rid of the state error, you need to add one more integrator, then it will be gone, or lamp input. But you have to be very careful because 2 integrator is 180 degree shift and the time delay, then this kind of have a reason. So it's very careful with that. Now theoretically, you can get it done. Okay? So you can show those kind of stuff and verify that, okay? And that's what. What is the pole and zero and closure? Now you can use MATLAB. So as long as you have a system here, now you can find the MATLAB. Now let's go to first of all here. Where is it? Where is the transfer function here? Here. Based on this one, I can calculate 4 and 0. So where I do it is like this. So there are three here. So I can combine this one. Okay? Using the method. Or you can use theoretical calculus. Probably to use method, so I'm going to make one by system 1, system 2, actually system 1, system 2, system 3, like this, okay? And then add parallel, okay? So system 1 is 5, oops, there it is, that's there, yeah. Okay, this one is transfer function 5 over s, right? So it's gonna be 5 over s, 1, 0, right? It's a transfer function. So 5 over s. Right? Let me. So this one is this one. So 5 over s. Now adding 40. So this 2 is 40. So that's constant, right? So you adding together, so let's call that the seed. This is parallel. This one is 2. So there will be 40s plus 5 over s, right? Now let's say this 3 is, I'm going to make this part. So it will be transfer function. Numerator part will be 10 and 0, right? That's the numerator. Denominator is 0.03 and 1. So like that. Okay? So now total will be transfer function will be adding previous one, right? So parallel system, I call this 3, so previous one 6, right? That's supposed to I added. After that I add 3, and I add this one. So your system is like that. So 10.12 x squared 4002 f plus 5 over 0.03 x squared plus 8. Now by looking at this, how many poles it has for this transfer function? How many poles? 2. How many zeros? 2 zeros, right? Got it? 2 0, 2 4. Yes.
But don't you also need to put this in series of the gen set transfer function?
I know.
Okay.
I'm talking over this one.
Okay.
Okay. Now I'm going to add. So this one multiplied by generator, exciter, multiplied by exciter 2. So I can use series. So this one is a series. I call this is series. So I'm going to have exciter called with transfer function. Transfer function. Actually, it's numerator is 1. Denominator is point. My case is 0.2 and 1. Right? That's the exciter. Right? So my generator will be. I'm going to do the same thing like this. Generator is 1 and 4. So I do have generator is this guy, exciter is 1 over 0.2s plus 1. So I'm going to make a series. Okay? So now total system transfer function. Okay, now I call the open loop. System is series. Let's add suppose 6 and exciter. Okay? And add together one more time. So let's do this of course. Open with this. So let's say over here. So this is PID controller multiplied by exciter. So I'm going to do one more time here. Now I'm going to multiply generator. So open loop and generator. So that's is purely so it's a four sort of system now. 1, 2, 3, 4. Yes. Okay? Until you typing now in the computer, you save all the comments. I have in there. Because there is history, right? So you can grab that. You don't have to type. Any questions to get this? Yes. Yeah, they might not know either.
I'm trying to figure out why I'm having there.
Okay. Any question here? Up to you. So what is the pole? How many poles? There are 4 poles. 1, 0, 2, 0. Okay. So how you find the pole and 0? Maybe this 1, 2. Okay, now let's have it. So I'm going to have loop 0044 4024 point A126 4.203 and 1 and 0. That's for you, right? So this one I wrote here. So first order, third order coefficient, second order, fourth order, and there is no constant procedure. So if you have this, then it gives 4 poles. Obviously 0. So 0 is there is 1 pole in the very left side, and 5 and 0.5. In fact, if you look it over, this one is, this pole is TD. One over 0.003, right? As I said, 1 pole, and this one is 1 over 0.2, exciter pole, and this is generator pole, 1 over 4. Okay? Because that's actually multiplication, right? 1 over PID will be 0.003 plus 1 and something there, numerator part, right? And there is 1 over 0.2s, my case is like this, and another one is 1 over 4s plus 1. So this is the feedback loop like this. This. So there is 1, 2, 3. There's the integrator. 1 integrator here and 2 0. That's why I have. This is your open. Any questions? This is the integrator. Yeah. This is the derivative term, the filter, right? Local filter, high constant. One over this side. Right? And this one is exciter. Oh, this is generator. Actually, if you put in the S plane, there's 1, 2, 3, all the way here. So this is S equal to 0. This is S equal to minus 0.25. And this is S equal to minus 0.15. And this is S equal to minus 333 like that. So that's what I mean. This is the PID pole. And this is the generator pole. Actually, this is what we are next section, chapter 5. This is the exciter pole. This is the derivative filter pole. It's a way that side, so actually this doesn't play the role. Okay? Then we find the poles. Now how to find the zeros? Let's go to the function one more time. Open loop pole. Right? So open loop. This look right. This one. So I'm going to find the zeros. So loop. So now it is 10.12, 40.02, and 5. So there are 2 zeros. So it will be 3 minus 3.825 minus 0.1292. So one of them is here. And the other one is 3.2, so it will be here. So this is a 0. I called this is PID 0. Okay? So you find poles and zeros. So these are open loop because the only thing is what is there. So how to find the closed loop?
That it's similar to you still have the closed loop function in this case will be the same numerator and the denominator plus like
so we do have open loop right here. It's big for us. So our case is like this, right? Plus and minus. The big one here and c equals to minus 1. Right? So we can make feedback. Right? We can make a feedback system. It will be hard to do it. Okay, now closed loop form. Closed loop is feedback. And open loop. And it will be feedback, so system minus 1. This is real feedback.
yeah.
Yeah.
So, got it? So you have this is a closed loop system. So from here, if you look it over this, so this is same as before. Right? Open loop 0 does not change. Okay? 0 is always stay there. Only thing changes is the pole. So you can find the closed loop pole based on this. How you get it? Same thing. Good. 0.04, 024, right? And A126, 14, 32, 41, 02, and 5. So, your zero is the new cruise loop one is so now 330. So this is cruise loop 4. One here. One is minus 14, so it will be here. Minus 14, or 9 something. This is minus 320. And minus 3.41. So it's going to be here. And it will be here. So your pole will be this, this. So original system, open loop system is this. Your closed loop will be like this. Okay? But you can use MATLAB. That's the way we learn how to generate, right? So same MATLAB command, just matter of the different value. Okay? Any questions? All right. So now next one here. So now investigate noise. Number 4. Okay? Based on test, loop stability criteria. Is a stable system or not? Obviously stable, right? Because we already verified it's a simulating, so it should be stable. But let's check it out with the loop stability test. Okay? That's what I mean, loop stability criteria. You can tell. Okay? And now adding noise, 5% and 10%. This day is every controller is a digital controller, right? So you guys have a 382, now it's a 382, it's the embedded system. Microprocessor is 382, 282? 381. Yeah. So you guys know how it's an old embedded system, right? So it's all digital. So there is a minimum significant bit. That means you have always truncation error there. So truncation error add this one. What is the truncation error? Actually you can have, it has a uniform random variable. You can consider it a uniform random variable. So I'm going to add here, add noise on this side, feedback system. Here, now, let's add noise here. And so we're going to select, where is it here? Okay, similarly here, there is a still source there. Uniform random variable should be uniform random variable, right? Random number. So add it here. Well, let's swap this one. And then Flip flop. So now it should be plus. Plus minus, it doesn't matter actually. So adding noise. So now I'm going to add the noise. And output is from generator voltage, right? You're adding noise. The with noise, your measurement area is here, like that. Okay? So that's your system. So if you run this one, actually I didn't set up, right? Let's go to, instead of this one, let's go to set, again. Set. And let's make this one to plus minus 5. So it will be 0.05, 5%. 0.05. Sampling time is 0.001. Right? So let's learn this one. So your response will be because of noise. A little bit wiggling here, right? The effect of noise. Okay? So now you can add 10%, so 0.01, 1, and 1%. 10%. So your response is like this, because of a noise. So you can see the noise here, right? Effect of a noise. Okay? So you are using the uniform random variable, okay? And you have to ensure the magnitude is correct. Now, load number 13, find performance of this one. Load disturbance of 0.5 apply. So let's go to your disturbance is somewhere here, right? Still I got it here. So I'm going to make 5%. So let's say about 5 seconds later, maybe. And the time is 5, initially 0, about final time is 0.5. So at 5 seconds, it will apply disturbance. Okay? So let's learn this guy, what happened here. So this is the effect of the disturbance with noise. Yes?
Can you click on your uniform random variable?
So 10% error.
What is seed? What does that mean?
Seed, you can change, you can depend on seed. Method actually has a problem with this one. Before, if you random number starts from the something, it is the same seed number, it will always generate the same thing when you run. It used to be whatever you actually get the random starting seed number based on the power supply output, something like that. But these days they have same seed number and same number, always same sequence. I don't like that, but they do that. But the seed number, where you're gonna start. So basically, they have a sequence of the random number, sequence of random, seed number 1, seed number 2, either starting from here or starting from here like this. It so depends on seed number. But if it's really random, it should not. Usually, it's just the real noise, pick for one of the value, arbitrarily. So every time you run it, it should be different noise. But if you have same noise, every time same noise. I don't like that. But that's the way it is now. Method.
Okay. That seems kind of silly to all have the same speed, but oh well.
But you can control it. You can have different seed numbers if you change it. Okay? So that's the effect over there. So you can study on how to do it. You can study on this one, okay? Now it's a matter of this one. Just change your value and see what. So 1, 4, I go to 1 and 6. Instead of 1 and 6, I go to 2 and 7. Okay, 2, 7. So let's go to 2, 7. So I'm changing this to 2, right? So you can learn it. Your response will be bad, obviously, because it's different. You need a different controller, so you need to adjust the PID, right? To make it go down, somehow make it fast, somehow you need to see. That's a trade-off. It's not going to be difficult because you have a reference already. So if you have this, what are you going to do, first of all?
Increase KP until it happens within 0.2 seconds.
Okay, so increase the KP. So you play with a little bit on that one. So about 200. So make it faster. Okay, looks like faster now, a little bit. And then what you need to do, increase KD. The too much overshoot. So I can make it faster. On the other hand, you overshoot increase. I can reduce that one, so I can increase KD. So now KD, I think 10 is not enough. So I 50, for example. I just pick a number. Good response. Still, you need more.
100.
So it will be 100. So about right? And then you can add, space is already reasonable. So that's okay. So you can play with it. Okay? So you have two different systems you can play with it. In fact, you can find out if it's large time constant, you have to make it high gain. Right? So time constant is big, that means it's a huge. So you need to more power, basically. That's why KP is increased, right? You need a turbo engine now. Hummer is very heavy. Okay? Yes.
When you changed the time, like when you were looking at system 3, where exactly did you make the changes at?
C3? What do you mean C3? Okay, now for MATLAB, I already got it here. So you can have, actually, not easy to do it. If it's the same controller, only thing I can change is, I can start it from, go back to this one. Exciter was, I can start with, okay, parallel is the same thing, this one is the same thing. So let's start with this side. This one. This is KP gain, so make it parallel. And this one is, make it this one. This is for the TG term, right? KG term, derivative term. And then make it parallel. So your exciter will be instead of this, I'm going to have exciter is different. So instead of 0.2, it will be 2. And now I'm going to have a generator. Where is it? I can go back to whatever it is. Okay, now generator. I'm going to have, instead of this, generator is 6, right? I select the 6 here. So now I'm done with up to generator.
It's 7, I think.
So now you can do open loop, and make it series, open you find the loop, you can find the open loop, and loop is very different, so closed loop is like this, so you can. So basically, once this settled, click, that's it, right? Oh, you can have MATLAB command, okay, like this. Instead of keeping this one, I can do like this. Can make script file here. So this one is a tensor function. 1 and 0.2 and 1. I'm sorry. And I can have system. exciter. How about that, exciter? This is the exciter. So I can make a copy this one. First, generator is, it's got a phone. And what is the PID is, let's say what PID is, sensor function. Okay. Let's say what 2, 4, 5, and what is it? It's 0.03, 1, and 0. Like this.
They get an extra bracket in your
No, not.
On the,
I can run it, see what, there you give some
Oh,
answer.
yeah.
If there is a problem there, help me. Help me, okay? So I can have it here, so I can find out if there is error or not. So I can run it. Oh, there is error. Okay, line 1 has problem, unbalanced. Line 1 has problem. So it's a function.
I think form is 4.2.
Should be
No,
right.
no.
Right? So run it, it gives exciter, generator, transfer function. So open loop is, it is exciter, generator, and one more series. And PID. It's still this way. So you have open loop here. Closed loop. So I'm going to have it here. Close the loop, close the loop. Or down, what is it? The feedback. Open loop. So now it's as a matter of you change this guy, you done.
Could I see the original schematic for the exciter and generator?
Okay?
Just for a moment, so just want to see if I have a question on it.
Okay. Yeah?
Yeah, okay.
What?
Okay.
Problem?
On that one, I don't think so. Can I see the generator?
Generator? Same thing. I have 15 minutes. So now, anybody didn't get the PID now? You block. Which team? You guys have PID? You got it?